So the today's topic is about the equivalence of PDA to PDA and the context-free grammar. Here we are going to see about how the conversion from PDA to CFG is done. So we have already seen how a PDA is accepted for the given context-free grammar by empty store and by accepted by the final state. So we have proved the equivalence between them also. So in last session, on last video, we have seen how a context-free grammar is equivalence is created for a PDA by accepting with the empty store. Now today we'll be seeing about for a given PDA the equivalent context-free grammar is generated. So the PDA which is given is accepted by empty store and we are going to find the equivalent context-free grammar. Now let us consider the PDA. So let M be the PDA which is accepted by the language using empty store, okay, which is accepted by the empty store. So now we are going to construct the CFG. So we are going to construct a grammar G, okay, with 4 tuplets V, T, P and S, and we have to show that the language G accepted by the context-free grammar must be equivalent to the M also, NM. Now we know what is V is, so let us consider V will be having a starting symbol and you will have a union with a triplet format. So you will be using a triplet. Here is Q naught, okay, you will have it as Q, comma, A, comma, P, okay, right? So this is a triplet where Q and P that will be belongs to the set of states in the PDA, and where A is and A will belongs to terminal symbols, okay. So A will be a terminal symbol. So what will be the terminal symbol? We will know is if so it is going to be nothing but the set of terminal symbols of the PDA. So it is equivalent to set of terminals, and the start symbol is yes. So we are able to know what are the non-terminals and terminals and the start symbol from the PDA. So the only thing we have to find here is we have to find the production rules. So rules in the production must be found out. So must be found out. So let us write the productions one by one. So we know the start symbol. So all the productions will be starting from the start symbol. So S tends to, we'll use a triplet. So Q, you will have some Z naught. So Q from, and the top of the symbol, that is the empty symbol that is available in the stack, is going to be Z naught and P, okay. So you will have for each P it can be in some K values, okay. So this is going to be an unit production. So when stack is empty, so we'll take when the stack is empty, it is accepted, so it will be accepted. So we are not going to care about what state we are in, okay. So we don't care about what is the end state is, since we are going to accept. So here we'll write it here. So we accept the language by empty string, okay. So it's empty store, hence we don't care about which state we are. So we don't care about the states in the production. So if you have a transition function, okay, so I'll write if a transition function tau of Q naught comma X comma A contains a state P and with some productions up to some BM, then okay, here X and x can be, it belongs to either a set of terminals or epsilon. Okay, we'll take it as epsilon. So x can be either a terminal or it can be an epsilon. Then the protection P contains, so what it contains is, so you will write in the form Q naught A some QM. So I don't know what state it is, so we'll write it in this fashion. So how do I write the rule is, so see here, this is how we are going to write. So string will be in the front, then you are starting from some state P1 and you will have B1. I'll write it here B1. I leave some space, then you will have B2, then you will have B3. It goes up to some BM. So if there is a transition function from the state Q0 for a terminal symbol X and with the top of the stack as A, then you will be going to some state P with some B1, B2, BM. Okay, so this B1, B2 will be a non-terminals. So how do you convert this transition function into a protection rule? So you will write Q0 with the top of the symbol and QM, so it can be of any state. So then this protection must be represented. So I will represent the string over here, that is the terminal symbols is represented here. Then it starts with some state and it goes on here. So what will be, this is starting state and the transition state must be written because it's a triplet. So from the, what is the protection mean here is, from Q I'm going to the state P for the stack input Z0. Now we know that we are starting from P and we have top of the symbol is the some non-terminal on the stack. So what will be the next state? So here I will write in this fashion. So it is going to be Q1. If it is Q1, the second protection on the right hand side will be also having Q1. Now you will have here Q2, this will be Q2, this is Q3, then the next protection will have Q3. So the final one is, if it is Q1, what will be the previous one? It will be equal to Q minus 1. So see here, this is how it is written. If you write Q1, the next production starting state will be also Q1. If the production is Q2, then starting state will be Q2. It goes on like this. So let us see an example. So you are given with a PDA. So you can see M is the PDA, and which is accepting the strings with empty store, and we are given with the transition functions. You can see you have two states here, Q0, Q1. The terminal symbols are 0 and 1. And what are the symbols on the stack is, it's Z0, Z0 and X. So you are given 6 transition functions and you are going to find the protection rule for the given context-free grammar. So first step, we are going to construct CFG G. So what will be G is, so G will be consisting of set of non-terminals, terminals, protection rule and starting symbol. So let us write the terminal symbols. So the terminal symbols are going to be, you know that it is going to be S, and we have seen in the previous slide that it will be having triplet format in the protection rule. So you will, in the your starting state also will be a triplet. So here you can see what are the triplet symbols you have here. What are the terminals, what are the states we have? We have 2 states, okay? So Q0, Q1, okay? Then similarly you have 2 symbols, okay? That is Z0 and X. So Q0, Z0, Q0. So you will have 2 to the power of 3 combinations. So another one is Q1, X, Q1. So how do we write it? So you have to write the combinations for Z0. So let me write it. So it is going to be Q0, Z, Q0. So that is one combination. The second combination is Q0, Z, Q1. Then you can have a starting Q1. So Q1, Z, Q0. Then you can have Q1, Z, Q1. So now we have done with the 2 symbols and 1 stack symbol. Okay. So you can see 1, 2, 3. You will have 2 to the power of 3 combinations letters here. So totally 8 productions has to be written over here. Next we will write for X. Okay, so now what is written here is for X, Z0. So write it as Z0 here. Okay, so Z0. Now similarly you will write it for Q0, Q1, X. So we will start from Q0. Q0 X goes to Q0. It can go to Q1 also. Similarly, Q0, so not Q0, it's going to be Q1. If Q1, then from Q1 to Q0 you can have, then Q1 to Q1 itself you can have. So these are the non-terminal states we have for our context-free grammar. Now what are the terminal symbols? It will be equivalent to the sigma of PDA, so which is going to be 0 and 1. And what will be your start symbol S? So start symbol S will be same as yes. Now we have to find the production rules. Right, let us see the production rules. So let me take the easiest part first. So I'm going to take 3, 4, 5, 6. You can see it's just a pop operation. That means my production rule is going to produce only the terminal symbols. Okay, it will be either an empty epsilon or it is going to produce a terminal symbol. So let me take this 4 transition alone. So I am taken its 4 transition. So you will write the triplet. So you can see here for state Q0 with the terminal symbol 1 on top of the symbol X, you are going to pop 1 from the stack. Okay, so you will be popping the from the operation. Though that means, so you will write it like this. So if it is Q0, right, so for the third rule I am writing over here. So I will write it as a triplet format. So what is the starting state? It is Q0 and the stack symbol is X, and we will be going to Q1 for 1. Okay, so for this input 1 it is going to be popped, so that will produce 1. Similarly, this expression for fourth expression you will write it as Q0 X Q1. It produces, okay, sorry, function name I have to check. It is Q1, so I made it here wrong. So let me change this. This is Q1 because both are identical, right? So Q1 X Q1 will also produce 1 over here. For fifth expression, the triplet format is Q0 for the symbol X, and it goes to Q1 for epsilon. Similarly, 6, the production rule will be Q1 Z0. Again, Q1 will also tends to epsilon. Now we will take the other transition function. We will start from first function. So what is the first function? It is Q0 0 Q0, which goes to the state with Q0 and X Z0. So we are going to take the first transition over here. So let me write the transition. So if you have a set of non-terminals in the bottom, so you will be writing in this fashion. So let me write the formula first. So how do you write it? So for Q0 Z0, we don't know what is the end state, so let me leave it as. So the production will be for which symbol it is going to be happening. It is for 0, so it is 0. Again we will start from which state, I don't know, and the end state also we are not sure. So how to write this is, so what state you are writing over here, it should be same over here, and what you write over here must be also same over here. So let me write and show you with the different colors. So you can see you will have, if you have Q0 1 2 3, then you will have nearly 8 production combinations. So here we are sure that we know that the starting state is Q0 and stack symbol is Z0. So the only thing is we are not sure about what is the end state is. So it can have Q0 or Q1. So let me take Q0 first. Okay, so I will take Q0. If this is Q0, then the last state should be also Q naught. So I will rub this here. So make sure. Okay, now this, if it is Q naught, then this should be also Q naught. Now what will be the value for the intermediate ones? It can have Q naught and it can have Q1. So let me write the Q naught first. So if this is going to be Q naught, the next combination I'm going to have here is Q1. Okay, so Q1, Q1. So I can have two possibilities. So because why I am writing in this fashion, if once it is coming over in the end state, the next production rules, it should be the starting state. So what happens here for Q naught, you will have two set of production rules. So I will take it as Q naught and Q naught. Now let me take another color. Let me write it here. So it's going to be, if it is Q1 and the final state will be also Q1. So I can have another two combinations, because one for Q0 and another one is for 1. So whatever comes as a last, it should also come as last. So the intermediate states, it can be of any states. It can be done with any possibilities. So let me write it for Q0 first. So this will be Q0 and this will be Q0. And this will be Q1 and this will be Q1. Why? Because if you have this, and this should be written. Now we have written for case for the transition function, first function. So you can see we have done for first function. Now we have to write for second function. So let me write it here. So what is the transition function? If your starting state is Q0 for the terminal symbol and the top of the symbol is X, then it contains, you will be staying in the same state, but you will have two XX. That is, you will have a transition to two states. Okay. So now we have to write the function. So how do we write the function? As I said before, Q0 and X cannot be changed. So for the initial state X, I don't know what is my starting state is, which provides, which implies the terminal symbol 0. With the triplet symbol, we start from Q0, X, and we don't know what is the intermediate state, again X. So first X comes over here, the second X comes over here, and you don't know what is the starting state. So let me finish. I will write the everything here. So Q0, comma X, Q0, comma X, and Q0, comma X. So you can have any possibilities. So let me write that first, all the four possibilities. So how you did for the thing, the same thing we are doing over here. So Q0, comma X, Q0, comma X, Q0, comma X. Then you can have a box, and intermediate, again it can be X. So let us consider my last state is Q0. So if I take Q0, the last state should be also Q0. So intermediate state can be Q0 and Q1. So I will have two cases. So I will write Q0. The intermediate one is going to be Q0, and here it is going to be Q1, Q1. Right. The next one is, my intermediate state can be Q1, the end state can be, final state can be Q1. So you will have Q1 over here and Q1 over here. Now intermediate can be Q0. So you can have Q0 and Q0 and Q0 and Q0. So now we have derived all the possible production rules for the given transition function. Now we should cleanly look into all the combination. There will be no rule such that, there is no rule such that you have a transition from a final state to the initial state. No PDF will have a transition from final state to Q0. Hence, the production rule containing such triplets should be removed. Hence, the production rule contains such triplets must be removed. So I will write it as must be removed. Okay. So let us see what are the combinations we have. So let me take a color. Okay, I'll take this color. Now Q1 to Q0. You can see here this is having Q1 to Q0. Hence, this transition, this production rule is not taken up for our process. So it is not taken up for our process. So we are going to leave it off. Similarly, here also you can see Q1 to Q0 we have a transition, hence this production rule also will not be taken. So we will write here, I will write here since Q1 to Q0 not possible. Okay, so we have cancelled it. Next thing we have to check here is, so I will write it over here. A transition Q0 x Q0 derives 0 Q0 x Q0. So what do you mean by this is, it's a left regression. Okay, it's a left regression equation. You can see Q0 x Q0 will be again and again, it will be replacing the same production rule Q0 x Q0. Hence, such productions can be removed. Hence, such productions can be also removed. So can be removed. So we will see what are the productions are like that. So 0 x 0, you can see you can't have 0 x 0. So your start and end symbol is similar. So we will remove this production also. Okay. Similarly, you can't have a production similar to that fashion. Okay, here it is Q0 Q1. So Q0 Q0 Q0. So no production can have a production to itself. It's a self regression. So we'll remove this also. Right. So if you have a production 0 x 0, or if you have a production 0 z not 0, that production rules must be also removed, because it is having a self transitions. Okay, so it is going again and again to the same state. So you will be removing such transition from the diagram. So only the transition available is this. Similarly, in the first state, you can see 0 x 0 is there. So you have a production here that is 0 x 0. So you will not be considering this step also. So you want to have a reference. So I'll put into mark alone. Similarly, you have Q0 x Q0 here. So you will not be having this step also. So all these key productions are not considered. Only the last production alone will be considered. Okay, the last productions alone, it is considered. Now let us write down the production rule. So what are the production rules we have? So we have this 4 production rule plus this one. Okay, I have this one. So we'll put like this. Okay, so we have this one. Similarly, we have this one. So we have 6 production rules. So let me write the context-free grammar for G with set of V, T, P, S. So we have seen what is V, T, P and all in the previous first itself. So if you want to write it, you can write it over here. So I can show you. So I have written V, T and S. So now the only production rules alone has to be written. So I will write the production rules. So the production rule is the start symbol. It is going to be S, Q0, Z, Q1. Okay, so starting state, final state, and it is Z0. So the top of the stack symbol, initial top symbol of the stack. Now we will write all the rules. So for case 1, the only leftover is Z0 tends to Q0 x Q1 and Q1 Z0 Q1. Right. Similarly, you have another production. So it is going to be Q0 x Q1, which gives again 0 Q0 x Q1 and Q1 x Q1. Then other productions you have is q naught x q1 will give 1, and from state q1 x q1 also will give 1, and for q1 x, okay, it is q naught, no, it is 1 only. Okay, q1 x q1, q naught 1 x gives 1, q naught x gives q1. Okay, this q1 x q1 can be an empty epsilon. Similarly, the last production is from q1, again end state is q1. For the non-terminal symbol z0 also tends to epsilon. So this is the equivalent context-free grammar for the given PDA, right? So if you want, you can see here, we can minimize it. So how to minimize the start symbol is, so the start symbol q0 z0 q1, which is a regression from this. So I will have a color over here. You can see it is containing this one. So I will update s tends to 0 q0 x q1 and q1 z0 q1. So we know q1 z0 is going to tends to epsilon, because you can see q1 into epsilon. So we will update the rule. So 0 q0 x q1, I will write epsilon for our understanding. Now similarly, q0 x q1, what is q0 x q1? It is, okay, it is going to be 1. So this can be repeatedly. So q0 x q1, you can see over here, it can be recursively written. So multiple zeros can come first. So you will have again 0 0, again q0 x q1, again you can see q1 x q1 is going to be an epsilon over here. So this term and this term, they tends to epsilon. So these are can be done recursively. That means I can derive O into O power m of q0 x q1. Okay, now the q0 x q1 can have another possibility, so that is 1. So it can be of 1 also. So your final grammar is produced is O of m and 1 of n. Okay, so that is the language that is generated by the PDA and which is accepted by the CFG. So let us see the proof how it is done. So if a PDA is given, the transition function must derive to a string, a set of terminal symbols. If and only if you have a transition function such that q comma x comma a, which can be derived to p comma epsilon, because if a string is derived from a PDA, then that string must be accepted by empty store. So that means finally the stack must be empty. So this has to be done. So in order to prove this, we have to prove in both the directions. So let me take the first direction, that with the starting state, with the input string and the top of the symbol of stack, we are going to find out we can derive to a set of terminals. So let us take the base condition. So what will be your base condition is the tau of q comma x comma a, which will be equal to p of epsilon. So I will take it as that if you have an input string x, then you will do a pop operation. So how do you write the production rule? As I said before, this is starting state, this is end state. So the triplet will be q and p, and you have to consider the top of the stack. So the top of the stack will be a. So this is the triplet and the rule will be epsilon. So it means that we are going to pop a symbol from the stack. So here we will take it as an induction. So we assume that it is true. Okay, will be assume that above is true up to I minus 1 steps. So we will be considering, so we will take an induction that this above step is true for up to I minus 1 step. Then we must prove So then we must prove the ith step. So we must prove the ith step. So let me write q comma x comma a if it derives p epsilon epsilon. Okay, so p epsilon epsilon, and if x is a leftmost derivative function, so we have seen it in the last video, so if you want you can just refer. So a will belongs to set of terminal symbols, or it can be an epsilon, where y will be containing the leftmost will be a non-terminal, will be followed by alpha. So you will be writing like this. So it will be a alpha dash. Okay, so alpha dash. Again, a will be a non-terminal, and alpha can belongs to V union T. So this everything we have discussed in previous one. So you can write q comma ay of a contains some production rules have been derived, or it can derive to other right hand side productions. So you will have q1 b1, or okay, I'll take it as beta 1, beta 2 up to beta m. Then q comma ay a can be derived to q1 comma beta 1, beta 2 up to beta m. So we have seen already a diagram, so we will put a graph and we will explain. So we have seen in the previous lecture also. So if you are consuming a leftmost derivation in beta 1, so when it before comes to the beta 2, the beta 1 part will be, so you will be like beta 1, beta 2, then you will have y2. So beta 1 will be consumed in this part, and you will be left over with beta 2 and y2. When you are coming over here, beta 2 will be consumed and you will be left over with only beta 3 and y3. So it goes on continues up to beta I passes. The finally you will be having only q yi plus 1, that is empty string will be carried out. So I will write in this fashion. So if it is qi yi and beta I can derive to qi plus 1 epsilon epsilon. So all the non-terminals have been consumed. So for the ith step, qi comma yi comma beta I can derive to an yi. Okay, so now with this term, so what I can say over here is I'll write it as q a y a contains such a form, that is, it implies a string a, that is the leftmost non-terminal symbol, followed by y1 beta 1 up to triplet format. No, so okay, I'll write that triplet format in separate side. I don't want to write it confused over here. I'll drop all this because so let me write the triplet form, that is the production rule. So we know that it contains beta 1 beta 2, and we can derive to OA alone. So what I do is I will write it in the triplet form. So you will have q a p, that production can derive a. So a will be the leftmost terminal symbol, so which will be processed. The leftover will be q1 and y1. Okay, not y1, so y1 is only this one, so beta 1 and q2. Similarly, q2 you will have beta 2 y3, and it goes on up to qm beta m and qm plus 1. Okay, so this term is ym, this is y2, and this is y1. So you can see I told you QAY contains Q1, beta 1, beta 2, beta M. So that is converted into a production rule here. So this is implied from AY1, Y2 up to YM, which can be derived to AY. Hence, we can write the production rule Q, A, P can directly derive AY. So what is AY? AY is nothing but X. So X is the AY. So X is the given input string. So we have proved one way over here. We'll see the next way, that is we have to say that both the directions we have to say. Now from this transition function I proved that a production rule can derive a string. Now from the production rule which derives a string, that should be converted into a transition function. So the second way we'll be doing it. So we'll see the second case. Now if there is a production rule that can derive to a string, then you will have a transition function that can derive to a pop-up operation. So use the induction. So I'm going to use the induction. What is the induction I'm going to use here is the number of steps, okay, in the derivation. So in what are the number of steps we are going to use in the derivation of the grammar to derive a string. So we are going to consider with the number of steps. So let me consider the base step. If it is the base class, if it is I is equal to 1, okay, so that means Q, A, P can implies X means, then you can write Q, A, P derives X, where X belongs to a set of terminal symbols, and it can be an epsilon also. Now coming from the mapping function, so we'll see the mapping function for this. So what will be the mapping function with this production rule in PDA? So the mapping function is in PDA, the mapping function is going to be, that is the transition function tau. So tau will be, it's from Q for the input X with the top of the symbol A, I will perform P epsilon. So it's a pop-up operation, okay. So this is the for the base condition, right? So if this is done, then tau Q, X, A can derive P, epsilon, epsilon. Now we will come for the induction portion. So we have proved the base condition, that is for the first step. Now we have to do for n-1 step. So we are going to consider up to I-1 steps. So how we can derive to a string. So this must be proved now. So let me write the triplet rule. Okay. So Q0, A, P, which implies a terminal symbol, and if it is a leftmost derivation, then it will be beta 1 Q2, Q2 beta 2, Q3 beta 3, okay, sorry, it is beta 3, Q4, it goes on up to QM beta M, QM plus 1. So this we have seen in the previous one how it is derived. So using several production rules, we are trying to derive a string, and each production rule is a leftmost derivation is used. So if that is the case, so you can see this one will be Y1, this is Y2, and this is Y3, it goes on, and this will be YM, okay. So you will have it in this fashion. So X will be equal to AY1, AY2, something like that. So now you can write a step QI beta I QI plus 1, which can be derived to XI. Okay, so since A is equal to, if X is equal to a leftmost derivation function, means a string can be derived from a leftmost derivation y1 y2 up to ym. So the ith production can be done. So with this I can tell that qi comma xi comma beta I can be a qi pop-up operation, qi plus pop-up operation. So what you are writing, qi for the symbol for the input x, and for the final state beta I, you will be resulting in non-terminal symbol. So that will be a pop-up operation over here. So what will be the for ith step? So it will be qi comma xi comma beta 1 beta I plus 1, and it goes on up to beta m. So okay, it will be beta m over here. So this can be derived to qi plus 1 epsilon plus beta I plus 1 to beta m. Since this entire portion will be erased in the stack, so this will be in the stack and it will be erased fully because PDA is accepted with the empty store. Now we have to write the mapping function. So the transition function should be written. So we have derived for ith case and I minus 1 case. So let me write the transition function. Okay, so for this we are going to write the transition function. So let me take it as 1 over here. Now for this, what will be the transition function? You will get q naught for the input a and the stackmost symbol x. Then it will derive q1 comma beta 1 beta 2 up to beta m. So starting with q naught comma ax1 up to xm, then a, it can derive to q1 comma x1 to xm comma beta 1 comma beta m. Right, by the induction hypothesis, because of the induction hypothesis, so I can say this can be derived to q2 comma x2 to xm comma beta 2 to beta m. So this again will be erased and it will be carry on. So when q2 is processed, you will have q3, then the leftover will be is x3 to xm and that beta 3 to beta m. So when you come to the last state, it will be derived to qm xm beta m, and finally it is going to, all the strings or terminal symbols are going to be consumed. So you will have p comma epsilon. So we can write, if you have a triplet q comma a comma p which derives to a string x, then I can tell q comma x comma a, which that can be also derived in PDA to a pop-up operation. Hence S derives q naught comma z naught comma p, which can be derived to the string x if and only if q naught comma x comma z naught is going for a final pop-up operation or empty of the stack. Okay, so this will be your final state, that is empty store, making up empty store, and this will be your initial ID. So the initial ID is this x, and will be the initial ID. So now I have proved in both ways how the problem is solved. So that's all about the equivalence of PDA and the context-free grammar. So we have seen how the conversion of context-free grammar to a equivalent PDA by accepting empty store. Similarly, the equivalence of for between the PDA and context-free grammar is also proved in this lecture. That is a PDA which is accepting string by empty store. From that, I have found out an equivalent context-free grammar. So thank you. We'll see you in a new topic in the next session.